Next, let's go to point 3. So I call this point 3. By the way, if you're enjoying what you're watching so far, please hit the like button. That way you support the free content we provide in this channel. And if this is your first time here, please hit the subscribe button so you see more videos like this. Or before we go to calculate point 3, because we don't know what the quality of the fluid is in here, so we could quickly go to calculate point 4, because we know at this point the quality of the fluid is 1 and we can find the pressure at point 4. So let me change this to point 4. So at point 4 we know that our T underscore 4 is equals to the evaporator temperature, the flash evaporator temperature. Yeah, the flash evaporator temperature. With this in mind, we can now calculate the pressure at point 4. So I call this P underscore 4. Again, I follow same process. So I just copy all of this and paste it here same way I did in the previous one. So here, rather than have T underscore 2, we have T underscore 4. And then here, rather than have 0 as the quality of the working fluid, we have to specify it to vapor, because the saturated vapor fluid enters the turbine. So we change this to 1. Then we can go ahead to calculate the enthalpy, the entropy, and the density at point 4. So I just do the same process, and we have here H underscore 4 equals, so sorry, I have to change this to S, which is the entropy, and change this to H, which is the enthalpy, and change this to the flash evaporator temperature. And then we can as well calculate the density at point 4. And then we change this to D. Again, we need to specify our units. So this is entropy, becomes joule per kilogram per Kelvin, and this becomes joule per kilogram Kelvin, and this one becomes, so I copy here and paste it here, kilogram per meter cube. So we now know our parameters in point 4. So I will just quickly go to point 6, which is also easy to calculate because we know at this point the fluid is saturated liquid coming out from the separator. So we could go ahead and calculate point 6. So we could go ahead and calculate point 6. So again, I change this to point 6. Point 6. So I'll quickly enlarge all this, so, and then do same thing for this. So again, we know that at point 6, the temperature is also the same as the evaporator temperature. So the temperature at point 6 is equal to, yeah. And then we know that the pressure at point 6 is equal to this pressure at point 4 and at point 3, because this is a constant pressure line. So we could say at point 4. So with these two information in mind, we can now find the H6. You can find H6, which will be, so I copy one of these, and I'll come here and paste it. So this is my H, but here we have T6, which is about the same thing as T4, but let me put it for clarity. T6, and then the quality of the fluid at that point, at point 6, is 0. So I change this to 0. So I could copy this, and we'll repeat the same process for the entropy. paste it, and then change this to S for entropy. And as well, we could do it for the density. 6. So I change this to D. So with this, we now know all our properties at point 6. Then we can now calculate the properties at point 3. So I change this to point 3. So at least we know that at point 3, our T underscore 3 again is equal to the evaporated temperature, the flash evaporated temperature. We know that our P underscore 3 is equal to P6, P underscore 6, which is also equal to P4. And again, one thing we know here is that because at point 3, this process, you have a throttle valve, so which reduces the pressure coming in from the heat exchanger into the separator. So the pressure here is reduced. So this is a throttle valve. And if it's a throttle valve, it means that the enthalpy at point 2 will be equal to the enthalpy at point 3. So the enthalpy here is the same as the enthalpy here for that throttle valve. So I could specify that H underscore 3 is equal to H underscore 2. So now we could quickly calculate the quality of the fluid. So let's find out what the quality of the fluid is at that point. So we could call this as Q underscore 4. And there are two ways we can calculate the quality of the fluid here. We could use the enthalpy relationship to calculate the quality of the fluid, or we could also use the CoolProp fluid properties to calculate the quality of the fluid. So I will just do both so you can appreciate that you will still get the same result. So first I will use the CoolProp property, fluid property. So this becomes equals, so I copy here one of these, copy, and I paste here. So one thing I need to change here is because I'm looking for the quality of the fluid, I could call this Q. And then because I know what the enthalpy at point 3 is, sorry, this should be Q3, I beg your pardon. So because I know what the enthalpy at point 3 is, so I could specify the enthalpy and then I can call this H underscore 3. And then I can use the pressure since I know the pressure at that point. So we could go whichever way. We could either use only the pressure at the temperature to obtain that, but we've already started using the enthalpy. So you could use any of the approach as long as you know two parameters in there, then it becomes a lot easier to obtain that value. So I will use the pressure, but to use the pressure, I would specify, say this is pressure, I will specify the phase of the fluid. So at this point, this fluid will be mixture of the saturated and the saturated vapor and the saturated liquid. So I can refer this to be two-phase. So in CoolProp, you need to specify that to be two-phase so you can be able to obtain the right parameters that we are looking for. So I'll close this and then call this P underscore 3. And that's it. So the other method I told you we could also use, and you still obtain the same thing, is to use the enthalpy relationship. So to do this, let me call this as Q test. Let's call it Q underscore test. So our Q test will be, so we could say H underscore 3 minus or subtract H underscore 6 all divided by H underscore 4 subtract H underscore 6. So this way we have also specified the quality of the fluid. So this result and this will still give you the same thing. So we could go ahead and find the entropy if we want to find the entropy knowing this parameter. So I can call this entropy to be x underscore 3, and I'll just copy this and paste this here and call this S. So you could either use the quality of the fluid that you now know, or you could still use the same thing here. You're still going to obtain the same result irrespective of which route you choose. So let's find the density, and then we do the same thing as D. So now we now have the parameters at 0.3. So one thing we could not calculate again is the mass flow. So remember, we specified that the mass flow coming in from the heat exchanger into the separator is 1 kilogram per second. But at this point, the mixture is separated into vapor and into liquid. So we need to identify what mass flow of that fluid goes in as vapor and what mass flow goes in as saturated liquid. So to do that, we already know what our quality of fluid is at this point. So we can now obtain the mass flow at this point and the mass flow at 0.6. So I'll call this mass flows. So let's call the mass flow into the turbine to be m underscore 4. So we call this as m underscore 4. It becomes m underscore 4 equals q underscore 3 times the mass flow, mass underscore f, of the fluid coming in. Then similarly, the mass flow at 0.6 becomes 1 minus q underscore 3 multiplied by the mass flow coming in from the pump. So again, we need to specify our units. So this has to be, I copy this and paste it here. Sorry, I need to change this. I didn't change this. Sorry, we need to get this properly so we don't miss our units. So this would be kilogram cube. This is Kelvin and this is kilogram. Yeah, so that unit is correct. And for our entropy here, I copy this and I paste it here. For the density, I'll copy this and paste it here. For the pressure, we have Pascal again. And for our temperature, we have Kelvin. So repeat the same process here. And do this here. And why for the mass flow, we have the unit in kilogram per second, same as this, kilogram per second. So next we go to 0.7. So we now know 0.6, next we go to 0.7. So let's specify 0.7. 0.7. Again, I would make this bold and then do the same thing for the mass flow. So at 0.7, we also see that there is another throttle valve here. So it means the enthalpy at 0.6 will be equals to the enthalpy at 0.7. So we could start from that. H underscore 7 is equals to H underscore 6. And then we also know that this fluid comes back down to the condenser pressure. So the throttle valve brings the pressure down to the condenser pressure. So we can specify that P underscore 7 will be equals to P1. But at the moment, we don't know P1. Interesting. So because we don't know P1, So we need to obtain the value for P1. Since we know the temperature, so we can find the pressure. So maybe we just go straight to find 0.1 characteristics before obtaining 0.7. So let's change this to 0.1. So we can just find 0.1 and then we can go ahead and work on 0.7. So at 0.1, so I'll just take all this off. At 0.1, we know that I beg your pardon, at 0.9. So we'll change this to 0.9. So at 0.9, we know that T_9 is equal to the condenser temperature. So we've specified it here, which is the condenser temperature. So it's going to be condensed T. Therefore, we can find P_9. We can find P_9 on the basis that this fluid here is at a saturated liquid. So we could use Q equals 0. So I'll just copy one of these for P9. So I just copy one of these because that's what I'm looking for the pressure. So and I'll paste it here. So that's P9 and this becomes at T9. Similarly, we can obtain all the values for the enthalpy and the entropy. So I just enter here and put my enthalpy to be this. I change this to H for enthalpy and it looks fine. And then I can do same for entropy and then I change this to X. And I can do same for the density and I change this to D. So with this information, we could now go ahead and calculate the properties at 0.7 and at 0.8. So let's go to 0.7. So like I said previously, that at 0.7, the enthalpy at 0.6 is equal to the enthalpy at 0.7. So we could specify that here. H at 0.7 is equal to H at 0.6. Again, we are missing our units here. We just have to be consistent with those units so we don't get it wrong. The pressure is in Pascal. This is in joule per kilogram, Kelvin per Kelvin, and this is kilogram meter cube. So here we need to specify the unit. This is joule per kilogram. And then now we know that P_7 is same as the pressure at 0.9. And again, the mass flow at 0.7 is the same mass flow at 0.6 here. So we need to specify the mass flow. The mass flow at 0.3 is the mass flow of the fluid. So M3, M_3 is equal to this, and the unit is in kilogram per second. So we've already specified our M6, we know our M6. At 0.4, we already know our 0.4. And at 0.2, we know that the M2 is equal to M_2 is equal to M mass flow, which is in kilogram per second. Here we need to specify the units in Kelvin. Looks good. We need to specify the units in Pascal. We need to specify the unit in kilogram per second. Yeah, we could go on here to calculate the quality of the fluid at that point. But again, we know that the fluid is in its liquid. Yeah, so we could just go ahead and do that and probably use it as a test for our temperature. So we could go ahead and say the Q7 Q underscore 7 is equals. So I just copy one of these. I can paste this here. And here I have it as H7. And here, because the fluid coming in is in its liquid phase, so I can just change that to liquid. And then I can specify the pressure, which is P7. Ideally, we know that T underscore 7 is meant to be same thing as the condenser temperature. So we could do a test to confirm that. So to do a test with this quality of the fluid we now know, we can also calculate the temperature. So let's do a test there. I will call it T underscore test. And then I will use this relationship here to find what that temperature is. At the end of the day, I'm still going to get the same temperature as my T test and T7. So I'll call this to be T. So this is just for test purpose. So what else have we not calculated? So we need to find T5 or properties at 0.5. We now know 0.4, 0.3, 0.6, 0.7. So we are left with 0.8, 0.5, and 0.2. So let's go over to 0.5. 0.5